أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته.
وعليكم السلام ورحمة الله.
Alhamdulillah, thanks to Allah subhanahu wa ta'ala for all His blessings and bounties that He has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Which of the blessings of your Lord will you both deny and insan deny? We need to make shukr to Allah subhanahu wa ta'ala who has given us iman. To believe Allah subhanahu wa ta'ala with all His powers, with all His qualities, with all His control. We need to make shukr to Allah subhanahu wa ta'ala that He has created us in the Ummah of Hazrat Muhammad sallallahu alayhi wa sallam, the best of all the Anbiya alayhim Islam. They came to existence to guide the humanity from Adam alayhi Islam till the last messenger Muhammad sallallahu alayhi wa sallam, so that each and every mankind could be successful not only in this life but the life hereafter. All the Anbiya alayhim Islam, they came to existence. They used to work on the hearts of the people so that it could be inculcated into the hearts of the people that the sole Khaliq, the Malik of this whole universe is Allah subhanahu wa ta'ala. Nothing can happen without the will and wish of Allah subhanahu wa ta'ala. It comes in hadith more or less meaning, there is a piece of body in the body, there is a piece of meat in the body. If it is corrected, the whole body is corrected. And if it is corrupted, the whole body is corrupted. Make sure this piece of meat is your heart, is your heart, is your heart. So we need to make an effort so that I, my family, my locality, at large, each and every mankind on the surface of the earth could be successful. The success of the life hereafter inside of Allah subhanahu wa ta'ala, that's what we are looking for. So inshallah, learning, talking and propagating it will be very, very beneficial for all of us. So let's start with today's lecture. If you remember from the previous lecture, we discussed one of the transformation, Laplace Transform. So what the transformation is, we normally transform a function or an equation from one kind to another kind. In other words, we could say that this transformation will reduce certain problems which we do not know how to solve them, or which are very complicated to solve, into problems which are relatively easier to solve. So that's what is the objective in mathematics. Generally, we transform, we reduce certain problems into much easier form. From there we get down with the solution, and then the inverse of that transformation, because initially we apply sort of transformation. So to kill that effect, to go back to the solution of the original problem, eventually you need to apply the inverse of that one. Laplace transformation is one of the efficient method for solving initial value problems. Idea is that the Laplace transformation will take us from initial value problem to algebraic, and then from the algebraic problem, much easier to simplify them by using those usual algebraic methods, and then the inverse transformation will take us back to the solution of the given problem. So if you remember from the last lecture, I got an idea about the schematic pictorial representation of this Laplace transform method. We will be having initial value problem. That's what the ultimate objective. This symbol, a special symbol L, so stands for Laplace transform. So it will take us from initial value problem to algebraic problem, and then we will find the solution of that algebraic problem. Since this solution is not the solution of the given initial value problem, at its present form. It's a solution to the algebraic problem. So the inverse of Laplace eventually will take us back to the solution of the given initial value problem. So these two intermediate parts, the algebraic problem and then the solution, they will play the role of bridge between the problem and the solution, applying a Laplace and then the inverse of Laplace. So quite a few things to be implemented when we look into this schematic. When we look into the overview of this whole method, so means we need to know Laplace transform as well as we need to know the inverse of Laplace. And that's how we started off. We started off with the definition. What the definition is there, if there is a real valued function f of t for all t greater than or equal to 0, multiplied by e raised to power minus st, on top of that integrated from 0 to infinity, we say that there will be an outcome in the form of a function of s, f bar of s, a special one as a symbolic representation. We say that it will turn out to be Laplace transform of the original function f of t. One thing, t has been replaced by s, and since it is not the original one, like f of t is there, so we have different notation f bar of s. The process of finding the Laplace transform of a function is known as Laplace transformation. Just like the heavy hitting theories, differentiation, integration, in calculus, calculus is all based upon the rate of change, remember? But with the rate of change, we move on to derivative, the instantaneous rate of change, and then the process of finding derivatives will take us to differentiation, and finally many applications are there, and then the reverse process of differentiation will take us to integration, and finally many applications are there. So they are all based upon the rate of change. So differential is an operator. So we know that differential does hold the linearity property. We also know that the integral, symbolic representation, also holds the linearity property. What the linearity property is there? If you have multiple terms over there, so we can separate this operation on each and every term, pretty much on the same line. We say that Laplacian, that operator is also linear operator. I mean, for example, we have a combination of two functions, f1 of t, f2 of t, real valued functions are there. So Laplace transform will be performed against f1 of t and f2 of t individually. So this is known as linearity property. So we just separate them as a linear combination. And then we have gone through with Laplace transform of certain functions. Constant is there, c upon s as a function of s. Exponential function, here you go with the exponential function, e raised to power at. So the outcome as f of s will be 1 upon s minus a. You see, t has been replaced by s, but it is going to be entirely different in comparison of f of t. F of t is e raised to power at, and f bar of s is an entirely different expression. So this is how we have f and f bar, two different symbolic representations. Proof is there. Laplace transform of trigonometric functions, sine of at, a upon s square plus a square, cosine of at, s upon s square plus a square. And they are closely resembled sine and sine hyperbolic, cosine and cosine hyperbolic. So sine of AT is A upon S square plus A square, whereas sine hyperbolic of AT would be A upon S square minus A square. Only this negative sign is different from the sign that has been utilized for sine of AT. Plus sign is A in the denominator. So now we are having minus sign. Laplace transform of polynomial functions. So whatever the function is A, I mean, as a very special case, if n is equal to 0, it will turn out to be a constant value 1. So 1 factorial upon s raised to power 0 plus 1. So 1 upon s. So it is also the justification of this one. If you take C, 1 for example, so 1 upon s would be the Laplace transform.
Sir, a question.
Yes, please.
Sir, if there is a sine hyperbolic ax, the variable is x,
Yep.
then we will multiply with e raised to power minus sx.
No, if you remember from the definition, what we say about the variable of integration, we say that it's a dummy variable. There could be f of t, f of y, whatever you name it. So it's a dummy variable, could be replaced by any other symbol. So it won't affect the outcome.
Sir, it's a constant or variable?
Which one?
Sir,
Which one?
S
is going to be variable.
T also variable.
Yes.
Sir, if there is f of x, then we will write sx.
If there is f of s,
F of x.
So
yes,
it will turn out
then
to
we
be sx and then f of x, and the variable of integration
sir.
would be x. All right. So if you look into the message again, what the message is, we need to know Laplace transform. We also need to know Laplace inverse of different expressions, different basic functions, exponential, trigonometric, hyperbolic, constant, polynomials. So these are the objectives behind the scene. Sometimes we could have a product of them, product of exponential and polynomial, product of exponential and trigonometric, for example. So chances are there we could have different expressions. So we need to build a foundation behind the scene to get to know the Laplace transform of those basic or elementary functions behind the scene. So that's what we are looking for so far. Exponential function, trigonometric, hyperbolic, polynomial. So if you summarize them in the form of a table, so you see that 1, 2, 3, they are all been described inside number 4. I mean, they could be obtained, number 1, number 2, number 3, from number 4 by varying the value of n. If n is equal to 0, so you are talking about 1, f of t as 1. If n is equal to 1, so it will turn out to be t. So you can find an expression from here. Same is the case for t2, 3, 4, 5, whatever it is. So few of them are listed. The basic or the elementary functions are been listed over here in this table, but it's not the exhaustive list. There could be a chance of having a product of e raised to power at times t, for example, e raised to power at times t square, for example, as we have seen in the case of higher order differential equations. The right hand side, f of x, could be a simple expression, one single factor, but that factor could be a product of more than one factors. So criterions are there, and we have seen that variation of parameters is a better option in comparison of undetermined coefficients once things are more complicated. So same is the case. We could have a chance for f of t to be a bit more complicated in comparison of those listed in this table. So this is all. We have to move on to build more formulation. Depends upon the scenario. For example, the scenario could be like e raised to power at times f of t. So product of f of t times e raised to power at. So this one is being the expression for e raised to power at f of t been obtained by utilizing first shifting theorem for Laplace transform. You don't need to, go and then prove it every time. Rather, we will utilize the statement. What the statement is there, what the message behind the scene is there. If you know the Laplace transform of f of t, then the Laplace transform of e raised to power at times f of t would be f bar of s minus a. You see, the outcome is closely resembled. F bar of s is the Laplace transform of f of t. And then if f of t is multiple of e raised to power at, then the Laplace transform instead of f bar of s would be f bar of s minus a. A is the scalar multiple of t in that exponent. So much easier to remember this formula. So whatever the expression over there f of t, if it is multiple of e raised to power at, so the outcome corresponding to the Laplace of f of t would be f bar of s minus a. So proof is there. Since we know by definition Laplace of f of t is equal to f bar of s. So here is the formula, the expression for integral sign from 0 to infinity f of t is multiple of e raised to power minus st dt. Now multiply f of t on both sides by e raised to power at. So inside these curly parentheses e raised to power at times f of t. So same is the case with f of t, e raised to power at times f of t. We have the same base, combine them. So it will turn out to be minus s minus a t. Now, if you follow this definition, the definition states that if f of t is multiple of e raised to power minus st over the interval from 0 to infinity with variable of integration t, it will turn out to be f bar of s. S is that one with negative sign multiple of t. Now instead of s, if it is s minus a, so pretty much like that, the outcome would be f bar of s minus a. So the only difference between this expression from here to there and that one is instead of s, now we have s minus a. So by utilizing this definition, the outcome or the expression for this integral would be f bar of s minus a. That's what we say. Yes. The Laplace of e raised to power at f of t is f bar of s minus a. So it will prove first shifting theorem for Laplace transform. So it's very handy. There are more than one. So this is how it is known as first shifting theorem. Using first shifting theorem, we have to show that e raised to power at t raised to power n is equal to n factorial upon s minus a raised to power n plus 1. Now, if you go back to the table, you see what the Laplace transform for t raised to power n, it's n factorial upon s raised to power n plus 1. Now, t raised to power n is multiple of e raised to power at. So since we know the Laplace transform of t raised to power n being n factorial upon s raised to power n plus 1, So once we multiply t raised to power n by e raised to power at, then by utilizing first shifting theorem, what it states, e raised to power at f of t is equal to f bar of s minus a. What is f bar? It's basically corresponding to f. So corresponding to f in this case, which is t raised to power n, f bar is n factorial upon s raised to power n plus 1. So the only thing to be changed is s to be changed by s minus a. So if you combine e raised to power at, t raised to power n, the outcome is going to be n factorial. S is going to be replaced by s minus a. So directly, how convenient is. In one step, by utilizing the first shifting theorem, we can get to know the outcome. Things are a bit more complicated than those expressions listed in the table. It's multiple of e raised to power at, but by utilizing first shifting theorem, we can have an outcome in a relatively easier way by utilizing first shifting theorem. Now we move on one more step. Talk about differentiation, talk about integral of Laplace transforms. So normally when we talk about differentiation, we see that it will be multiple of t raised to power n, multiplication by t raised to power n. Theorem states that if we know the Laplace transform of f of t, if we know that is there, it's a symbolic representation, but if you take a particular expression for f of t, there will be corresponding particular expression for f bar of s. If we know the Laplace transform, then the Laplace transform of this combination in terms of derivative would be minus 1 raised to power n, nth derivative of f bar of s with respect to s. So this is how the differentiation is going to be performed when f of t is multiple of t raised to power n. So t raised to power n times f of t. In the previous case, we have seen that the first shifting theorem, we have e raised to power at, multiple of f of t. Now, f of t is multiple of t raised to power n, so it will take us to the differentiation of Laplace transform. So differentiation of Laplace transform, f bar of s is the Laplace transform of f of t, and then those derivatives performing them will take us to the differentiation. The process of finding derivatives will take us to differentiation. So this is the formula behind the scene. So before we move on, we look into the proof. So our target is to talk about Laplace transform of t raised to power n f of t. We start by looking into the definition. Laplace of f of t, f bar of s would be equal to an integral from 0 to infinity e raised to power minus st times f of t with variable of integration st. So is the definition. Then by Lebanese rule for differentiation under the integral sign, what the Lebanese rule, we haven't gone through, I believe. But anyway, Lebanese rule is basically the generalized form or the generalization of fundamental theorem of calculus. If you remember from the previous semester, we discussed fundamental theorem of calculus. What the theorem is there, we will be having derivative to the integral, integral to the derivative over there. What the generalization of that fundamental theorem of calculus is known as Lebanese rule. Or in other words, we say that fundamental theorem of calculus is a special case of Lebanese rule, where we look into the differential of an integral, where we perform differentiation on top of the integral. So derivative to integral is going to be done by utilizing Lebanese rule. F bar of s is this one. So just differentiating both sides with respect to s. So we need to, if you go back and recall fundamental theorem of calculus, so integral sign is there, and then differential is there, means derivative is there. So derivative and integral. So over here, derivative on top of the integral. So if you bring this derivative inside the integral, inside this one, since we know t is a variable, s is also there, so it will turn out to be partial differentiation. So bring this operator inside this one, so it will turn out to be partial upon partial s, because we have inside that two parameters s and t. So if you take the partial derivative of e raised to power minus st with respect to s, it will turn out to be e raised to power minus st times minus t, the further extension. So derivative to that exponent with respect to s would be minus t. So t is there, and the negative sign is adjusted outside the integral sign. Now effectively, again, if you go back to the definition, e raised to power minus st from the formula, t is the variable of integration, integral over the interval from 0 to infinity. So this whole thing is going to be f bar of s corresponding to f of t, corresponding to f of t. So it's basically Laplace of f of t. So here you go. All the essential components are there. Integral from 0 to infinity, e raised to power minus st, and then the variable of integration t is there. So whatever inside over here, so it is going to be the Laplace of this expression, just like the Laplace of f of t. No, it's t times f of t. So this is how we say that it's Laplace of t f of t, just following the fundamental definition of Laplace transform. Instead of f of t, it's t times f of t. So all the other essential components, integral, e raised to power minus st is there. So this thing inside the bracket will take us to Laplace of that t times f of t. Negative sign could be transformed to the other. So in this way, we have Laplace of t times f of t equal to minus derivative to a bar of s with respect to s. So what we need to justify, what we need to show, t raised to power n times f of t, Laplace of that is minus 1 raised to power n, ns derivative of a bar of s. So if you take n is equal to 1, so to the left hand side, Laplace of t f of t, to the right hand side, minus 1 raised to power 1 means negative sign, and then the first derivative of a bar of s. So this outcome is basically verified. It proves the theorem for n is equal to 1. N is 1 here, minus 1 raised to power 1 here, and the first derivative is there. So the theorem is proved for single or starting value of n. Non-integral value is 1. We also need to talk about for the rest of the values 2, 3, 4 up to so on. So how we do that, if you remember from the previous classes, the method of mathematical induction. So we will utilize that to establish the theorem. In general, for every non-integral value, we will utilize mathematical induction method. So what we do, initially we assume for an arbitrary value, k for example, we assume that this statement is true. This statement is true for an arbitrary value. There could be any value from these infinitely many values. K is going to be an arbitrary value. We assume that this theorem is true. Means if n is replaced by k, we have this statement. No, this is only possible if it is justified for the very next value to k. Means if it is justified for k plus 1, where we have k, if it is replaced by k plus 1, then we will justify that, yes, our assumption is true. That's what the mathematical induction is. We assume for an arbitrary value k, and then it will be justified if by performing one step. Wherever we have k, it is replaced by k plus 1. So how we do that? To the left-hand side, Laplace of t raised to power k f of t. So look into the fundamental definition. Instead of f of t, it's t raised to power k. So when we look for the Laplace, essential components are there. There must be integral sign over the interval from 0 to infinity, multiple of e raised to power minus st, that thing, whatever is there inside the curly parenthesis with variable of integration. That's the fundamental definition. So we need to justify this statement for n is equal to k. So what we do? We differentiate both sides with respect to s, taking derivative on both sides, or differentiating both sides with respect to s. Now, if you differentiate the right hand side once more, we already have kth derivative. So if you differentiate once more, so it will turn out to be k plus 1th derivative. So kth derivative of f bar of s is there. If you differentiate once more, just like the first derivative is there, if you differentiate once more, it will turn out to be second derivative, once more, third derivative, and then so on. So if the derivative is kth and you differentiate once more, it will turn out to be k plus 1th derivative to the right hand side. So differentiating the right hand side once more, it will turn out to be k plus 1th derivative. To the left hand side, derivative to the integral. So bring this one inside the integral, it is going to be partial derivative. So with respect to s, there will be an additional t, just like in the previous case, we have gone through with that. If you differentiate e raised to power minus st with respect to s partially, so it will turn out to be e raised to power minus st times minus t. So this minus, the outcome minus is there, and t is combined with t raised to power k. So it will turn out to be t raised to power k plus 1. We can shift this negative sign to the right hand side, combine it with that negative sign. So we already have minus 1 raised to power k. If you take minus 1 raised to power 1 to the right hand side, so it will turn out to be minus 1 raised to power k plus 1 now. Now you see that. Now you see that. Everywhere where we have k on both sides, it is being replaced by k plus 1 on both sides. K plus 1, k plus 1, k plus 1, k plus 1. And this whole thing to the left hand side, it's basically Laplace of t raised to power k plus 1 f of t. To the right hand side, minus 1 raised to power k plus 1, k plus 1th derivative. Which shows it, the theorem by mathematical induction holds for k plus 1. We assumed for k, and now it has been justified for the very next value, k plus 1. So now whatever the value of k is assumed, so it is automatically justified for the very next value, for the next value, and then so on. Thus the theorem is true for all positive integral values of n. So this is all we have justified. That yes, the Laplace transform of this combination of t raised to power n times f of t would be equal to certain order derivative of f bar of s. Now that order is going to be incompatible of that exponent of t. If there is one, so it means that we are going to talk about the first derivative. If n is equal to 2, so it means that we need to perform twice, and then so on. So they should be compatible with each other. And same is the case with minus 1 raised to power that particular value of n. Take an example. Use the above theorem, the differentiation for Laplace transform. We need to find the Laplace transform of t times sine of t. No, you see that it's different. Again, different from those listed in the table. It's a product of sine and t. And just we have gone through with the differentiation of Laplace transform. We will apply that rule, that theorem. But before that, we must know that the Laplace transform of f of t. What is f of t in this case? It's sine of 2t. We know the Laplace transform of sine of 2t, 2 times 2 upon sk plus 2 raised to power 2. It's basically, I mean, in the formula, it was, I think, a. So a upon sk plus a square. Sk means 2 raised to power 2, 4. We already know from the table, from the previous. So hence, by the above theorem, we have, if it is t raised to power 1 to the right hand side, again, keep an eye on the formula. If it is t raised to power n, we need to perform differentiation. We need to take only first derivative to f bar of s. What is f bar of s? It's the Laplace transform of f of t. In our example, f of t is sine of 2t, and we know f bar of s is 2 upon sk plus 4. And because n is 1, so minus 1 raised to power 1 means negative sign, and then the first derivative. That's what we have. Minus sign, minus 1 raised to power 1, and then the first derivative to f bar of s. What is f bar of s? F bar of s is that one, corresponding to f of t, sine of 2t. F bar of s is that one. So differentiate it. Differentiate this one with respect to s. So you will get down with that expression. How you do that? I mean, the derivative to this one equal to this one. Try that one. Try that one. In the meanwhile, I generate a poll for you people. So today is 10th of July, 2020. And we are looking for those who are present. No need of that. All right, so poll has been created for your attendance. All right, So we go back. Yes, how we do that? From calculus, if you recall those formulas, you could utilize quotient formula. Quotient formula. So apply the quotient formula or whatever the technique that you apply over there. It's up to you. Simple expression is it. Better off to apply the quotient formula to get down with this outcome. So pretty much on the same line, you can look into the Laplace transform of t square sine of 2t, t cube sine of 2t, and then so on by utilizing shifting theorem. So if it is t raised to power 2, so it means that you need to differentiate twice the Laplace transform of sine of 2t. So you need to differentiate twice. In other words, you need to differentiate this expression once more with negative sign from the formula. So differentiate this one once more together with the formula with the negative sign from the formula. So it will take you to the answer. One more step, one more derivative. Integral. We have gone through with the derivatives where we see f of t is multiple of t raised to power n. Now sometimes things are there that f of t is divided by t, then what could be the outcome? We say that it will be an integral from s to infinity of f bar of u du. So Laplace of f of t upon t will be an integral from s to infinity f bar of u du. Again, you see that du is dummy variable, and eventually the outcome is going to be f bar of s eventually, because the variable of integration is there, as the outcome is going to be f bar of s. U is a dummy variable of integration in this case. So we have gone through with differentiation. Now this one will turn out to be integral, but the variable of integration is u instead of s. Eventually it will turn out to be s because of the lower limit is s, provided that limit t approaches to 0 from the right hand. It's a right hand limit, positive subscript, superscript in fact, indicates that we are approaching to 0 from the right hand side. So if it exists, the limit of this fraction does exist. If it exists, only then we say that yes, the Laplace of f of t upon t will be equal to that. We look into the proof. So by definition, Laplace of f of t means that bar of s is equal to an integral from 0 to infinity f of t is multiple of e raised to power minus st with variable of integration st. So f bar of s to this one. So s could easily be replaced by u, yes, on both sides. There won't be any harm doing that. S is being replaced by u on both sides. Pretty simple. So by definition, we have this one. So if you replace s by u, there is no harm doing that. So f bar of u is equal to the integral. So what we do, we integrate both sides with respect to u from s to infinity. F bar of u is this one. On both sides, we integrate with respect to u from s to infinity. That's what we are looking for. We have, for example, f of u, and we need to get down with this expression with the integral sign variable of integration over the interval from s to infinity. So integrating f bar of u with respect to u over the interval from s to infinity means we have to integrate the right hand side as well with respect to u over the interval from 0 to infinity. So integrating both sides with respect to u from s to infinity, the limits of integration. So over the interval from s to infinity on both sides, to the left hand side, that's what we are looking for. And from the right hand side, we are expecting that this whole thing is equal to Laplace of f of t upon t. So this one is to the left hand side, yes one, and we will do everything to the right hand side. Interchanging the order of integration, yes, if you remember from calculus the previous semester, Lebanese theorem, we can reverse the order of integration provided that function of two variables is continuous over the rectangular region, because if you have one variable of integration, it is going to be a line, and if you have two variable of integration, it will be a rectangular region. It will be a region. Most of the time, it is going to be rectangular. I mean, if you go back and look into the double integral, the applications of integration, multiple integrals are there. So we can reverse the order of integration. So same is the case. What we are going to do, we reverse the order of integration. Now this integration is from t to u, remember, t to u. Initially, we need to integrate this expression with respect to t and then u. So this is the order of integration from t and then u. So what we do, we reverse the order of integration. We bring u inside the bracket and then t is outside the bracket. Means now the order of integration is from u to t. Since we are interchanging the variable of integration, so we need to interchange those integrals. So t is from 0 to infinity, and the variable of integration u is from s to infinity. So interchange them. Bring this integral inside, take that one outside, take this variable of integration outside, bring that one inside the bracket. So just reversing them. Everything is going to be reversed now. And then the integral of e raised to power minus ut with respect to u, because with respect to u, f of t is independent of u, could be taken outside the integral. So only you need to integrate e raised to power minus ut with respect to u. So integral of e raised to power minus ut with respect to u, e raised to power minus ut divided by the derivative to that exponent with respect to u. So the derivative of minus ut with respect to u would be minus t. So this is how we will be having minus t in the denominator. So upper limit will make everything 0 because e raised to power minus infinity is 0. With the lower limit, it will turn out to be e raised to power minus st divided by minus t. So t is there in the denominator, and the negative sign will be combined with the lower limit. For the upper limit, positive sign; for the lower limit, negative sign. So negative into negative is going to be positive. So f of t upon t. So now, if you go back again, the fundamental definition of Laplace transform. So we have three essential components: e raised to power minus st, multiple of something, with variable of integration over the interval from 0 to infinity. No, e raised to power minus st is multiple of f of t upon t. So it will turn out to be Laplace of this thing, f of t upon t. So this is all. It is proved that Laplace of f of t upon t is equal to an interval from s to infinity, f bar of u du, the integral of Laplace transform. Laplace of f of t upon t is an integral from s to infinity, a bar of u du. Using the above theorem, we need to find Laplace transform of sine of kt upon t. No, you see that entirely different. Initially, we started off with developing foundation about single elementary functions like polynomial, exponential, trigonometric. Then we moved on to first shifting theorem, multiple of e raised to power at, then further multiple of t raised to power n, and then now division by t. So if sine of kt is divided by t, we need to find its Laplace. So the condition is there, remember, from the previous theorem. The condition is that whenever we are interested to find the Laplace of this fraction, the limit to this fraction should exist. Only then this is going to be applicable. So initially we need to see, yes, there is a limit, finite real value. So limit t approaches to 0 from the right hand side, f of t upon t. What is f of t? It's basically sine of kt upon t. So it will turn out to be k. And on top of that, the Laplace of sine of kt, it's k upon sk plus ksk. From the table, the formula for sine of kt was equal to a upon sk plus hk. So the limit to this fraction does exist. F of t is basically sine of kt. And the Laplace of sine of kt means f of t is equal to a power of s, in this case k upon sk plus ksk. Hence, by utilizing this theorem, the Laplace of f of t upon t would be an integral from s to infinity, f bar of u du. F bar of u is basically the corresponding Laplace transform to f of t. Instead of s, it's u. What we see in this case, Laplace of f of t is equal to that one. So f of u would be equal to k upon u square plus k square. So with the interval from s to infinity du. So if you look into the integral of k upon k square, u square plus k square with respect to u, it's a formula there. X upon a, I mean a upon x square plus a square with respect to x. For example, from the calculus, the previous semester's course, we can look into the formula for the integral of this one. Anyway, so one of the formula, there could be chances of having more than one versions of the outcome. Anyway, if it is in terms of tan, so it will turn out to be tan inverse of u upon k. Apply the upper limit at the lower limit. So we know that tan inverse of infinity is going to be pi by 2. And then tan inverse of s upon k at the lower limit. So this is one of the version of the formula as an outcome. There could be a chance of having different expressions, but this is one of the possible expression as an outcome. All right, so unit step function, very vital to be discussed inside Laplace transform, because it greatly make an impact on the usefulness of Laplace transformation or practical demonstration will be highlighted by the the utilization of unit step function. What the unit step function is. So from the statement, unit 1 step, we normally take a step. So one step function, the unit step function denoted by UA of t is defined as UA of t is 0 if t is less than a, and UA of t would be 1 if t is greater than or equal to a, where a is going to be non-negative value. So this is the fundamental definition of UA of t. I mean, closely resembled with the definition of mod of x. I mean, mod. Yes, could be resembled with that. Piecewise function is a. If you look into the mod of x, so we will be having two pieces over there over a certain part of the domain. So for the first part of the domain, when t is less than a, the outcome is 0. For the second part of domain, different from the first part. So remember, when we look into the pieces of a function, corresponding domain or the part of the domain should be entirely different from each other. UA of t is 0 if t is less than a, and UA of t is 1, because remember we are talking about unit 1 at maximum. So it will turn out to be that fun. So if you look into the pictorial representation or the graphical view of this expression UA of t, so it is 0 when t is less than a. For example, a is that one, an arbitrary value. So when t is less than a, UA of t is 0, and we know that if you map on t-axis, because it is going to be dependent UA, independent t, so it is going to be the quadrant or the plane of t and UA, just like x and y plane is there. So on the real line, instead of x, we have t, and the outcome or the function is going to be UA being the dependent. So value of the dependent variable is 0. So we know that on t-axis, everywhere it's 0. 0, this dark line, this dark portion of the line is going to describe the value of UA. It is going to be 0 for all sort of values of t less than a, and when t is greater than or equal to a, UA of t is equal to 1. So that one. So if you scale down one here, so this is going to be the graph. So it's a pictorial representation or graphical representation of a unit function. We have taken an arbitrary value of a is greater than or equal to 0. For example, if you take a is equal to 0, for example, the unit step function has a jump of discontinuity. Yes, very vital to be noted down. So it has a jump of discontinuity of size 1 unit from here to there. So you see that this piecewise function is not going to be continuous. It has a point of discontinuity, it has a jump of discontinuity, but the size of this jump is going to be 1 unit from 0 to 1. If a is equal to 0, for example, then what will be the pictorial representation? So 0, u of 0t everywhere before t is equal to 0, and for all sort of values of t greater than or equal to 0, it will turn out to be 1. How do we look into that? I mean, for example, once more, if you take a jump at this point in time of 1 unit, so there will be another step, one more, another step, just like a ladder. You go upstairs by taking a step of 1 unit every time. So every time, one step will take you going upstairs. So one step, second step, third step, and then so on. So from here to there, and then from here to there, over here, and then one more step over there, and then so on. Ladder is there. So this is how you can somehow imagine unit step function. You take a step of size 1 unit every time. To move ahead by going upstairs, the unit step function is a basic building block of various functions and it greatly increases the usefulness of Laplace transform methods. So very vital. So it will improve, it will greatly improve the usefulness, or it will highlight the implementation of Laplace transform methods. The unit step function is also called, sometimes is also known as Heaviside unit step function. Why so? It's because of the name after the English electrical engineer, remember? So many of the inventions are there. Electrical engineer, are going to play a vital role inside mathematics, or mathematics going to play a vital role inside engineering sciences everywhere, in particular in electrical engineering. The foundation is there, the mathematics, and then build on that. You move on to the practical implementation from the daily life. So this unit step function is also known as Heaviside unit step function because of an electrical engineer, English electrical engineer, Oliver Heaviside. The era is from 1850 to 1925, around 75 years. All right, so we have gone through with the definition. Unit step function, UA of t. So its numerical value is 0 or 1. There is no other option, 0 or 1. So if you are talking about for a certain value, like a, e is less than a, unit step function is 0 everywhere before a, and it will be equal to 1 for all sort of values of t greater than or equal to a. So 0 or 1, 0 and or 1, these are the options behind the scene. So we need to show that the Laplace transform of UA of t would be e raised to power minus a s upon s as a function of s f bar of s. So then we will utilize this one for the rest of the part of this particular topic, the Laplace transform of a unit function. Look into the definition, fundamental definition. Since we know that UA of t is equal to this one, we have two pieces over there, and then apply the definition of Laplace transform on UA of t, whatever it is, inside those curly parentheses. So it will turn out to be integral from 0 to infinity, multiple of e raised to power minus st times UA of t with variable of integration. Now the interval from 0 to infinity been subdivided into two parts. You see, the point of division is a, from 0 to infinity, a is greater than or equal to 0. So you need to take start from 0 and up to what, so on to infinity. So what we do, we subdivide the interval from 0 to infinity into two sub-intervals, from 0 to a, and then from a to infinity. Yes, we can do that. If you combine them, it will turn out to be an integral over the interval from 0 to infinity. Everything is kept same. E raised to power minus st u f t with variable of integration only. We split the interval of integration, because if you go back to the fundamental message of integration, so we can do that. Yes, we can subdivide into pieces symmetrically the area under the curve. So yes, we can split into pieces. If you combine together, it is going to be 1 unit. So a is an arbitrary value in between 0 and infinity. So we can do that. So over the interval from 0 to a, from 0 to a, so u a of t is 0, and for all sort of values from a to infinity, t is greater than or equal to a. So the starting value is a up to infinity. So for all sort of those values, u a of t is 1. In the first integral, the value of u of a t would be 0, and for the second one, it is going to be 1. So over the interval from 0 to a, when t is less than a, means that interval u a of t is 0. There you go. And from a to infinity, u a of t is 1. Just replace them. 0 multiple of anything is going to be 0. 1 multiple of that is going to be there. Now integral of e raised to power minus st with respect to t. E raised to power minus st upon derivative to that exponent minus st with respect to t. So minus s. For the upper limit, it is going to be vanished, because e raised to power minus infinity is 0. For the lower limit, e raised to power minus 0. So remember, these are the limits for the variable t. T infinity means minus infinity, e raised to power minus infinity is 0. When t is 0, e raised to power 0 is 1. So 1 upon s, minus into minus plus from the expansion, and eventually we will be having e raised to power minus. Sorry, it has to be, it's a typographical error. That should be a, because for this one it was 0. So it's a, typographical error is a. So a is there, the lower limit. At the upper limit, it is going to be vanished. At the lower limit, so we will be having a. So minus a st is going to be replaced by, it's a typographical error. So make correction over here, it is a. I will do in the, for the next lecture, we'll make correction over here. So eventually we see that, yes, the outcome is going to be e raised to power minus a s upon s. Whenever we find the Laplace transform of a unit step function, the point of division is going to be key, a, as an arbitrary value. So it will turn out to be e raised to power minus a, that a, s upon s. All right, so that's it for today's lecture. We have gone through with the idea of Laplace transformation. We have gone through with Laplace transform of some basic or elementary functions. Then complicated stuff is there. Sometimes the function is multiple of t raised to power n, sometimes multiple of e raised to power at, sometimes it is being divided by t. So we will be having shifting theorem, differentiation, integral. They are all going to be counted, because as we have seen, in the case of differential equations, the right hand side f of x could be anything, simple constant value, exponential function, trigonometric function, polynomial of certain degree, or could be a product of e raised to power exponential function times another factor over there, like polynomial, trigonometric, constant value, whatever it is. So sometime it could be divided by t. So we have gone through that. Talking about different formulas, how eventually we are going to utilize them. If we have that scenario, we must have the Laplace transform for those scenarios. So we have discussed quite a few of them in this particular lecture, as well as in the previous lecture. So from the previous lecture until now, we are trying to look into the foundation of this topic, Laplace transform. So this is going to be the half of the part, remember? Initially, we need to talk about Laplace. Laplace, eventually, the initial value problem, taking the differential equation together with certain conditions. And so initially, we are going to talk about Laplace transform of certain combinations, certain individual functions over there. We also need to look into the inverse of that. Only then we will be able to capture this whole message. What the message is? We are interested to find the solution of initial value problem. We have to have an idea about the Laplace transform of basic functions, their combinations. We also eventually have to have an idea about the inverse of those basic functions as well as of those combinations. Only then we can get down with the solution of initial value problem. So that is the ultimate objective. We are interested to find the solution of initial value problem. So partway through the journey, we have to go through with Laplace. We also have to go through with inverse of Laplace. Only then we can compute the solution of initial value problem. All right, so that's it for today's lecture. If you have any query, we got some time. A minus sign is basically together with the differentiation, not with the integral sign. Different formulas. So minus sign only comes with differentiation. Okay, lectures are being uploaded. Few of them been uploaded. I will try to upload the rest of them over the weekend, inshallah. Okay, 183. 183. Talk to your CR for an assistance, how to mark your attendance. No, amazingly, if internet issue is there, how can you pass this message over here? I haven't marked attendance sheet due to unavailability of internet. I have passed this message. It is only possible with the internet.
Sir, there is a question.
Yes, please.
Sir, can you open the page number 3 of the slide?
For today's lecture. So,
yes, sir.
2 and then 3. Is this the one you are looking for? It's a linearity property.
Sir, where it is shown Laplace transform?
Sorry, say again.
Sir, where is written Laplace transform of trigonometric function?
Over here, there is no.
Sir, Laplace transform.
All right. I move forward. Here you go with Laplace transform of trigonometric functions. Is this the one?
Yes, sir.
All right. Yep.
Sir, ओके सर सर ये जहाँ पर ये प्रूफ लिखा हुआ है
Yes.
साइन ऑफ ए टी का लेप्लास ट्रांसफॉर्म करनी है
Yes.
सर इसमें हमने e की पावर माइनस एस ऑफ टी एस टी से कहाँ पर मल्टीप्लाई किया है
There could be more than one channels. Remember, there could be more than one channels. There could be more than one channels. Whenever we look into the proof, you could have alternative options behind the scene. We have done that behind the scene, basically. We have utilized this thing. Laplace of e raised to power at is 1 upon s minus a. I have added this slide over here, you see. Laplace of e raised to power at is 1 upon s minus a. Proof is there. So once the result is with you at your disposal, no need to go every time to prove all these things. So Laplace of e raised to power at is 1 upon s minus a. To go with the proof, surely you multiply it with e raised to power minus st. And eventually, here is the result. For the rest of the part, you just utilize this result. I have added this slide with the previous provided lecture. So we utilize that one. Laplace of e raised to power at is 1 upon s minus a. So here you go. Laplace of e power iota at would be 1 upon s minus iota a. Corresponding to that, e raised to power at 1 upon s minus a. So if it is iota at, it will turn out to be 1 upon s minus iota a. And same is the case with that one. Minus is there, so minus. So with that negative, it will turn out to be positive. Yes.
Sir, iota is considered as a constant in Laplace transforms.
Iota is an imaginary from complex number.
From the definition of constant, it is considered as constant.
Iota stands for square root to minus 1.
Yes, sir.
Yes. Iota square is equal to minus 1, absolute constant value. So what we do over here, we do utilize the definition, but since the result is already established, so we do utilize that result. All right, so do we have any other query? The poll is still there. I believe you can mark your attendance. So poll was generated and it's still active, I believe. It is still alive. You can mark your attendance right now. Okay, what else we have? No, there is no other serious query. All right, then thank you very much. See you inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.